stop cursing from now on.
But if you
a lot in teaching, because when I was learning quantum mechanics, I found that I go to these lessons, I know how to pass exams, but when you come to do something useful with it, then you actually need to understand it, and QTIP definitely helps with understanding quantum mechanics. So people are using it in research institutes, universities, but also we're aware that some of the big quantum computing people like Google and IBM, we know that they use it as well, and we also know that the people building quantum computers, they're using it, so there we go. So our admin team is all over the world. Most of them are currently in Japan, because that's where it started, and Franco has a lot of money, so he's got lots of them working as postdocs, but we also have a few of us in Europe, and one, I think, in North America, which always seems disproportionate. We're approximately 10 people, but it's, measuring it in terms of number of people isn't a very good measure, because, of course, some of us are only doing it for like 5% of our time, and then other people 50%, and some people close to 100. So we're supported by lots of different organizations. We're affiliated to NumFocus, but a special mention to Unitary Fund today, because, as I alluded to, they helped us with the awkward thing of having to pay for stuff in the world. So there we go. So these are the guys who started it, Paul and Robert, and Franco is the sort of, I don't know, we had to dream up some title for him at some point. I think we call him, oh no, he didn't like that. Project director, I think we settled on in the end. And so I don't know whether like 200 plus contributors sounds like a lot, but it feels like a lot to us. And so there are an awful lot of quantum physics researchers out there who did something in their PhD. They added a little something, and then they uploaded it to QTIP, and 3,700 citations. It's definitely a big number in the world of quantum physics. Certainly, I was very happy when we finally released a Quantum 5 paper, because now I get a citation a day. So there we go. And perhaps on the subject of learning quantum mechanics, there are like 100 plus tutorials. And so if you want to learn something about Rabi oscillations, we have a tutorial for that, and lots of others. Well, over 100. Oh, yes, should mention perhaps something that is sort of like numerically valid is this number of other projects which depend upon our library. And so perhaps this big one here, IBM Qiskit, well, you know, that's backed by IBM. But you'll see that we're right up there next to Google Circ. And, well, let's say we certainly don't have the same level of financial backing as them, but we are popular because people think it's useful and use it. So these are the current bunch of people. Not sure why I'm there first, but maybe I got there first. Eric here probably does more work than nearly all of us, but he's the shyest. Nathan's the most brazen, and he's currently at Unitary Fund. And who else should I highlight? Max here, obviously, is our newest member, which was kind of a surprise when we finally got a female member, which we were all very excited about, because Veronica just joined, and she's pretty much full-time, and she's great, and we're very happy. And then when we made her a member of the admin team, we were like, where's Max? And he's like, oh, he's not actually on the list. So we hurriedly brought him in officially, even though he'd been working on it for like 2 years or something. Anyway, probably, Simon's also worth mentioning, in that we met him. He gave a tutorial in EuroSciPy 2019, and we were like, who the hell is this guy, and why is he giving a tutorial on our software? So I hung around a lot with him and recruited him after the second day. So, and then he works for us, he did 2 years for us full-time and did an awful lot of good stuff. we have this thing called a board. We're not sure what they do, but some of them do stuff, some of them don't. But Will Zhang here is obviously helpful because he made Unitary Fund, which is very helpful. So this is a sort of graphic which tries to explain our library and sort of how it's structured. I might have to move over there because I can't read that. Let's have a look. So at some point, it all sat in one package, and then we were like, well, this has some like maintainability type issues. So now we have something that we call the Qtip family. So those are two things you see on the left in boldface. They're sort of like the functions of the core library, and so they kind of do the things which made Qtip famous originally, which is it solves various equations, which Max will show you in a bit. And then I made a module for a quantum optimal control. At some point, that required too many other dependencies. Eric didn't like it, so we moved it into a separate package. And then similar things like with supporting JAX, and then perhaps the most recent family member is this Qtip QQuantum, which is an interface into the NVIDIA thingy, and I was able to negotiate a GH200 as part of that deal, which I'm very proud of. And so perhaps the stuff at the top is a bit technical, but you can see there's a lot of functions there, which you might sort of like think, well, they obviously relate to things you can do with matrices. We are basically matrices operating on, acting on vectors. And then the other things there perhaps are a bit quantum mechanically, but probably you've all heard of entanglement, so we have ways of sort of measuring that and stuff. And then, so the sort of core of Qtip are these solvers, so the equations which Max will show you shortly. They're just basically first order linear differential equations, and then we solve them, using these various different methods. That'll probably do for now. And so, as I mentioned these different packages. There are more, but these are perhaps the most important ones. In particular, this circuit simulator, which is the thing which we decided to focus on for this tutorial, because it's the most sort of comp-sci kind of thing. So it's like one way of representing what a quantum computer does. So I think that's my introduction. So hopefully you did these things. Probably the easiest one by a mile is to use TryQtip, which runs Python. It's like a Python environment online already, and these tutorials are already loaded up on there. And I guess Max can show you exactly how to access those right now, and then talk you through the quantum physics and then how to use Qtip.
Yes.
Good?
So I think this is working.
Yeah. And so what I will do is I'm going to kind of like probably sit somewhere up there and or wander around and stuff. And if people look like they're stuck, I might, if they catch my eye, I will offer to help. But maybe I won't need to do much. Here you go, Max.
So yeah, there are several methods for you to access the tutorials. You can try, if you have fast fingers, to install it locally, try to copy the code from the slides. But we try to alleviate as much as possible from trying to understand the underlying quantum physics, but focus more on trying to experience what it is like using Qtip and seeing all these quantum mechanical phenomena. So when you go to TryQtip, you will find a folder that says tutorials. You double-click that. You find a folder that says EuroSciPy 2026. Double-click that. And then you'll find two notebooks. One starts with 01, and the other one starts with 02. And then you'll be able to run these notebooks in your browser. At least when I tried it this morning, it worked on my machine. It should be machine agnostic. So the idea is we'll go through a bit of the physics. we have some small tasks for you to play around with the parameters. But if you just want to see and experience what it's like in my daily life as a researcher, you can just hit play on those notebooks and, well, have a nice afternoon. So you can decide how much you want to involve. To start with the 01 underscore qubits notebook, we'll mostly be talking about two-level systems throughout this tutorial. So these can often be called qubits, and well, you know what bits are, I suppose. It can be 0 or 1. Famously, qubits can be also anything in between, people often say. So, you know, not only 0 or 1, but they can be in some superposition and only decide if they want to be 0 or 1 once I measure them. So we use a specific type of visualization for this, which is called the block sphere. So in QTIP, we have a native implementation of the block sphere where we can add these two-level system states. And you see, usually on the North Pole, we have the 0 state, which would correspond to also a classical 0 state. And on the bottom, we have a 1 state, which is also a classical 1 state. But throughout some computation or throughout some physical phenomena, our system might land in a superposition, as, for example, these plus and minus states are. So only when I measure them, they will say, well, now I collapse to a 0, or now I collapse to a 1. And the superposition is one of the many arguments why people say, well, quantum computing is fundamentally different and might give us like a certain quantum advantage. So some mathematical background, we'll not be able to escape this fully, unfortunately. But as Alex rightfully said, we'll primarily be multiplying matrices and vectors. And the matrices are going to be 2 by 2 or 4 by 4, and our vectors are going to be like two rows or 4 rows at maximum. But naturally, this all generalizes to higher dimensions, of course. So in QTIP, we can create these 0s or 1 states by using this basis function. And the first 2 gives you, to use physics language, the size of the Hilbert space. So it is 2 because, well, once we measure our qubit, it is either in 0 or 1. And they span our vector space. But as I mentioned, they can also be in a superposition. So we can create these plus and minus states by doing, in this case, this 50-50 superposition of 0 and 1. And naturally, as we've seen before, we can add them to a block sphere. And this makes it quite easy for us to understand roughly where we are. And So what do we see now? What has changed? Without interpreting it, just tell me what has changed, especially for the later times. Faster, okay. Yeah. Exactly. So before we had a convergence that will lead to complete energy relaxation, like both our qubits will reach the ground state. But now because we added also the back action from the environment, our state actually will go to zero because it will reach a different equilibrium because we've added another interaction with the environment. And we see that, well, this whole scary slide about Lindblad formalism was also, well, scary for me at the start. But with QTIP, we are just adding another list. We're changing S to an M. And there we have it. That's your second simulation done. Crazy. Wonderful. So, yeah, we have about half an hour left. So for the second part, this should conclude now the notebook, 0.0_1. We shall move on to the 02_ teleportation. And we'll look at something famously explored in your quantum information course at university, namely the quantum teleportation protocol. So it's called a protocol because, well, it's often used in when people talk about quantum networks or even quantum internet. It is unfortunately not yet at the stage where Star Trek is projecting it to be at some point. However, it was experimentally shown and by Anton Zeilinger in, I think, 2012. Don't quote me on that, but something around that time, where they were teleporting a quantum state from La Palma to Tenerife, so 143 kilometers. At that time, that was a world record. And it's quite an impressive experiment because you need very, very fine-tuned experimental setup. And they were shooting a photon into space and then back down to Earth, and all of that without losing quantum coherence. So this is really an impressive experiment. And the theoretical framework behind it is, in comparison, not so difficult. So for the sake of making pronunciation easier, we're going to replace La Palma and Tenerife with Alice and Bob, which should be a bit more familiar. And Alice and Bob want to, teleport a quantum state. And this teleportation is largely enabled by what we all know by entanglement. And we want to look at this teleportation protocol using these circuit diagrams. So maybe you've seen this in some quantum computation talks. They tend to get very large and very complicated very quickly. But luckily for the quantum teleportation, this is traceable within one lecture. And on the left, we see our good old Bloch sphere, which we've seen right at the start of the tutorial. So what we look at is this psi A. This is a state that Alice will produce. In your notebook, you will have a function that's, I think, like random state or something, which will just create a random state on the Bloch sphere for you. You don't have to worry about much. And this random state will then be transferred, that in the end, we will have a psi B. This will be Bob's state, and will be exactly teleported. So this will involve 3 qubits now. We don't have to worry about how they're interacting and stuff that we have now understood and we've put in our pockets. But Alice will use 2 qubits. Bob will have only 1, unfortunately. And we see right from this circuit diagram, what we will do is we will have Alice and Bob qubits interact at the start. So this is an interaction. Then, in principle, Bob can go on holidays to Tenerife while Alice stays back home in La Palma. And she lets this qubit interact with the other qubit. So this is, again, an interaction. We will then do some measurements. We'll have these measurements sent to Bob via mail, for example. And then based on these measurement results, where's my pointer? Bob will do some X and Z. We'll see what that means in a second. And then that's all we need to do. And Bob will eventually have the psi 0 state in this the Q0 state will be exactly in the Q2 state. Don't worry, we'll get through this step by step. All in all, to have some more scary math, teleportation protocol looks something like this. So Alice prepares a state psi A. Alice and Bob, so this subscript of A and B means Alice and Bob, they will share a Bell state, which is a very famous example for a maximally entangled state. Alice will do a Bell measurement, and then we will have classical communication of this measurement to Bob. And depending on the measurement result, Bob will do this X and Z to retain exactly Alice's state. So, step by step, let's first look at what this weird Bell state is. So Bell states are 2-qubit states. So just as before, we're now only involving two qubits. And there are 4 Bell states, and all of them are maximally entangled. Maximally entangled means that if I measure one, I can determine 100% what the other state is going to be. So if we look at this, at the red underlined state, for example, you see this is a 0, 1 plus 1, 0. What does that mean? The left number refers to the first qubit, the right number refers to the second qubit. So if I measure this underlined state, and my measurement result gives me a 0, because my superposition has collapsed into the 0, I know for 100% certainty that the other state will be a 1. Vice versa, when I measure a 1, I know with 100% certainty that the other state will be in the 0. And if you work this out, these states are complete in the sense that you cannot have more Bell states. So if you look at the phi plus, so the top one here, this just means, okay, I measure 1, naturally the other one will collapse to I measure 0, the other one will collapse to a 0 as well. So we use this maximum entanglement to teleport this state. So if Alice is doing her Bell measurements, that means that Bob's state will collapse, even though Bob is doing holidays in Tenerife. And this will enable us to do this teleportation. So this first part of the circuit is exactly about creating this Bell state. And in QTIP, we can build these circuits by using our QIP package. So this is among the QTIP family. Should be readily available in your notebook. And we have this circuit module with a qubit circuit. In this circuit, for the sake of creating simply these Bell states, we define a number of qubits, so n equals 2, and we define a number of classical bits. So we need a classical bit to store our measurement as 1. Then we can use this circuit, qubit circuit object to add some gates. So we have a SNOT object and gate, and we have a CNOT gate, where we just have to define the target, so which qubit this operation is acted upon. And for the second, because it has a control bit, we define the control. It will become clear in the next slide. So as promised right from the start, this is still nothing else but vector matrix multiplications. So our qubits are still vectors, and these gates are simply matrices that we multiply from the left. So this is what it looks like in a circuit. So we have our S0 and our C0 here. And we can add a measurement just by calling this add measurement function. We can give it a name because we like the letter M. We call it M. And yes, we store it in a classical bit. And then we have a very nice function to draw these circuit modules. So just to illustrate the power of this maximum entanglement, we said, we measure the wave function collapses, we can determine the state of the other. So we notice with this psi state that, sorry, I should start from the top. So we provide an initial state, just as before, we've seen that. And we can run our circuit with this initial state, just as before, only that now we call circuit.run. And then I provide this plot on block function to to plot the respective qubit states. This p trace is a partial trace. If you want to know more, you can ask me later. Right now, just take it for a mathematical feature. But eventually, it allows us to plot the 2 qubit states on the Bloch sphere, as we've seen before. And when we look at the psi plus here, okay, we talked about the entanglement. So we said that I measure 0, I get 1, or I measure 1, I get 0 on the other. But they're also in a superposition. So now it gets a bit complicated. So when you press run on your cell many, many, many times, and you plot it, what you will see is sometimes you will get the result that the green arrow is going up, and the orange one is going down, or the orange one is going up, and the green one is going down. And this is exactly this collapse of the superposition, or collapse of the wave function that we talked about. So in 50% of the time, because it's a 50-50 superposition, the first qubit will collapse to a 0, so it will point up. But when the first qubit collapses to a 0, automatically the other one will collapse to a 1. On the other side, the remaining 50% of the time, one qubit will collapse to the 1, and the other qubit will therefore automatically collapse to the 0. So I think that maybe illustrates entanglement in a quite nice way. So you can try this out. You can hit run on this cell a couple times, run your circuit, run this measurement, and eventually you will find these Bloch sphere and these states. Do they? So you can, if that happens, either I uploaded the wrong notebook, but it can be saved by simply, where is my pointer? Do you see my pointer? Yeah. If you change this 1 to a 0, or this 0 to a 1, you will get a different Bell state, therefore a different entanglement, as we've seen before. You know, we will maybe get a psi plus, or a psi minus, or a phi minus. You will just get it. And then, naturally, well, this will be a bit different. But you will for sure generate a Bell state, just a matter of which one you, yeah. All right. So we've at least a bit seen how entanglement can work, and we've nicely visualized this on a Bloch sphere. So we want to incorporate this now into our whole quantum teleportation protocol. So we're going to walk through this protocol and build our circuit on the way. So at first, in principle, you can do this later as well, but you know, we just start by state preparation by Alice. So we use this random single qubit state function, which I've provided you with, which is just going to give us some qubit state on this Bloch sphere. It will probably not going to be the one that I have. It's just going to be somewhere there. Yes. Then, just as before, first step, creating the Bell state. Now, of course, a bit more complicated because we have 3 qubits. So again, we'd use our qubit circuit object, n equals 3 this time, because we have 3 qubits. We also have Alice's second state. And for our classical communication, we need 2 classical bits, because we can measure 4 different Bell states. So to transport that information, we need 2 classical bits. Otherwise, this creation of the Bell state is the exact same as we've seen before. So we go on to a bit more in depth. We can talk about this more in detail if you want. But this second part here accounts to this Bell measurement. So this interaction term here, this C naught, and this S naught will do a basis change, and we will have the measurement to the classical bits. If you want to know the math, come to me later. For now, take it as this is our Bell measurement. So the result of this measurement will be communicated by 2 classical bits to Bob. So this is the third step, I think, in the protocol. And then Unfortunately, it's a bit weird because they are a bit to the left, although they should be a bit more to the right. We can add our X and Z gates on Bob's state. So we said Bob will invoke these X and Z operations depending on Alice's measurement result. So we can add these gates, X and Z, to Bob's qubit. So target 2 refers to the Q2 here. And we can have a classical control, which means apply this X operator if classical bit 1, so C1, is 1. And the same goes for the Z, only for now classical bit 0. Unfortunately, there is no line here. I don't know why, but it's just the case. From my understanding, there should be a line to the classical bits to make it easier to understand. But because we are in charge of our code, we know that this classical control is happening. Yes, so this is our circuit. We've added, using add gate, we added all these gates to our circuit. We added the measurements to communicate them to Bob. And what we can then do is run our circuit. So we have Alice state. So the state 0 will now be Alice state. That is the random state we have created at the start. And we just initialize the other 2 qubits in 0. That's just standard, I guess. And we can call circuit.run with our initial state to again obtain our final state. Then if you allow me again to use this p-trace, partial trace, to retain Bob's state. So this is just throwing away all the information of Alice's qubits. We just want to focus on Bob's qubit. So Bob's state at the end of the day is retained like this, and we can plot it in the exact same way. And what you will see is that this teleports the qubit from Alice to Bob, although the qubit 0 and qubit 2 have never directly interacted. So the Q0 is this Alice state, the one that we wanted to teleport. There is never a direct line to Q2, which is Bob's state. And with the additional fact that Bob can be anywhere. Bob could have been on the moon. And upon measuring, Bob's state will collapse. You send Bob 2 classical bits of information via WhatsApp. He does the X or Z rotations, depending on the results, and bam, Bob will have exactly Alice's state. So this is quite a phenomenal result in quantum information. What else can I say about it? Well, I think we will go to the last and probably most involved part. So what I want you to try is
able to run where we're up to so far. And are there any questions? Are people finding it sufficiently convincing that we managed to transfer a quantum state? Because I guess from the world of computer science, it's the idea that you can just copy a state. It's just, np.copy or something, but yes, this is a good question, because people sort of like think about this teleportation and they think, well, does this mean that we can transmit information faster than the speed of light? But then you identified that there is this classical channel which is limited by the speed of light, and hence Bell managed to resolve this massive argument between Einstein and the rest of the world of quantum mechanics back in the 80s or something, 70s maybe. So thanks. Okay, thanks.
Yes, thank you very much. So, yeah, at least according to my clock, it's 14 more minutes. So I think it's a good amount of time to invest in like the last part of the tutorial. Maybe Alex also has a few more things to say then. But for this part of the tutorial, I want you to try and use a different bell state. So before we've used, in a tutorial, we've used the phi plus. So that is the 0011. What I now want you to try is what happens when you use the psi plus that we have generated before. So I'm not sure if, so yeah. As I hinted before a bit, you can generate a different bell state by changing the initial state. So when we go back, here in our initial state, so state 0, we have Alice's state. This remains unchanged. But these two are responsible for the creation of this bell state. So changing one of them to, well, I would suggest changing this one to a 1. You will generate a different bell state. What that means, so if you change the last one here to, if you change the last one here to a 1, if I remember correctly, you should be generating this psi plus state. But then the protocol changes a bit, because what we need to add is another x here. So when we, spoiler. When we look at this from before, we have only x and z in the circuit, which are the operations that Bob needs to perform. But what we need to now add in front of all of this is another x without any controls.
Is that an uncontrolled X?
That's an uncontrolled
It's a
X.
straight flip, yeah, so
yes.
There's rightly no wire connection there.
Yes. So here we have introduced, so this is the old circuit, right? Here we have added the gate X with the target 2, and we have, this is already in place. We have this classical control. So now the X that we want to add before all of this is an X without the classical control. So you can just remove this and add it above. Don't change the other ones, they are still important. But it comes in 2 steps. So there is the first part that we talked about, you can test what kind of bell state you're generating. But I mean, I just basically told you, right? I would prefer you to change this to a 1, otherwise I need to adapt my slides. But if you change the last one here to a 1, you will generate this psi plus bell state instead. And then by adding this X gate in front of Bob's gates, you will hopefully again recover. I mean, I would invite you to try also before adding this X gate to see that the teleportation no longer works. Like on your block sphere, you should get like some states that go like nonsense. But then when you put this X gate, they should be aligned once again. Yeah.
Does it matter whether you have the X right after the C0, or can you do it at the end after that?
Let me think about that for a second.
Yeah, I would have thought it would only work if it was before. But,
if you run it multiple times,
there you go. You found something new. Write it up.
I would have intuitively said no, but no. Well.
So we have no X, not really wrong test, so it's supposed to be there, or whatever. If I understand correctly, there.
Can you try it with the randomized image?
How's it looking? No, definitely. Yes. Yes. So if you go up a bit, so this part, a bit up, a bit up. So this is our state 0, right? So this has, well, I call it psi here. This is the state that Alice is preparing. And now the Q1 and Q2, they're both in the 0. So try changing one of them to a 1 and see what happens. So because this is a 2, it's either 1 or 0. So the 2 determines we only have 2 states. So it's 0 or 1. Yes. It depends what kind of system you're trying to describe. Yes. And then, just run it and then see what happens, especially at the last plot. Yes. So now you see, because we have changed the initial state, it's no longer working. Because we have used we're now using a different Bell state. It's kind of dependent on the fact that we were using one specific Bell state. So now what you can try is putting an X.
I think so. Every time I run it,
X
it's different.
in front of
Run the whole thing.
this line. So this is when we're building the circuit here. Yes, so measure Bob side is exactly adding this X and Z. And you can try adding another X in front and removing the classical control. No, sorry, like you can copy this line and add it on top. And then remove the classical control. Like just remove that argument completely. Yes, I think that should be it. Okay, let's see what the initial state you've chosen. Can you go back up to your initial state? Yes.
Is everybody else? It's worth noting that you. These ones will only take effect. Okay, so I'm going to wrap up now. If you're still doing the exercise, then you can do like my students do when I give a summary slide, which is either just completely ignore me or start to pack away your things. So where do we get to? So this was some other exercise we were going to do. I got worried that we might not have enough material, but of course,